Okay, well, today I thought we would look at some more examples of trig sub and maybe an application to get us started. So I'm going to share with you Desmos, if I can find it. Where's my Desmos? Hang on just a second. Share, that's not. Is this it? That looks like our link. That's not, well, maybe that's, see if I can, oh, I wanted to share this window. Do you guys have Desmos?
Yes.
Okay.
Yeah.
All right, so here's the question. The question is, how do I find the area of a circle? That kind of seems like an important thing for math types to be able to do. And of course, you know pi r squared, but how do we know that it's actually pi r squared, right? I mean, we didn't actually prove that. We just had our third grade teachers tell us and we memorized it. And so I would like to see if we can prove that. That's kind of our plan. Make sense? Okay, that's the question. But let's even go one step further. If A and B are both 1, you know, when we have x squared over a squared plus y squared over b squared, then we just get a circle, right? Because if A and B are the same, okay, and they're both equal to r, then you can multiply by r squared on both sides. You get x squared plus y squared equals r squared. You get just a regular old circle. But if A and B are, say, different from one another, let's just make it something easy, then we would get an ellipse. So we can stretch it out that way, or we could stretch it out this way. And so the question then becomes, all right, you know, all right, how about we just find the area of an ellipse, and that would include the area of a circle, and we'll knock them both out at the same time. And as far as I remember, I don't know, anybody know the formula for the area of an ellipse? I'm getting no's, everybody's shaking their head. No, no one knows that, right? So circles, yeah, you memorized it in third grade, but ellipses, you don't know. And so what if we needed to do this? And now we do, because we got nothing else to do. We're all quarantined. So here's what I would do first. First, I don't like this whole negative, you know, negative, positive. I can't keep track of all that stuff. So I'm just gonna do 1/4 of an ellipse, right? Just do this section here in the first quadrant and then multiply times 4. Are we good with that approach? And we don't have to deal with, like, if we want to take the square root over here, we wouldn't have to worry about the plus or minus. We'll just stay in the positive quadrant. So what I want to do then is build a bunch of rectangles, add them up, right? Then get the area, take the limit as n goes to, the number of rectangles goes to infinity, and then in the end, multiply by 4 to get the whole ellipse. So what I would be doing is, you know, first I would put a rectangle in here that's about maybe 1/2 wide and 1 tall. So that looks to me like that area would be 1/2 times 1. So that would have an area of 1/2. And then I put another rectangle right in here, right in here, that was also 1/2 wide, but not quite as tall. Looks like about 0.95 maybe. And then this one would be about 0.87 tall. And then this one would be about, you know, what is that? 0.7 maybe. And then this one would be 0.5½. And then this one wouldn't be very tall at all if we use the right endpoint. Everybody good? Following?
Yeah.
Okay, awesome. So I'm going to switch back over to paper. Let's see, how do I get back to paper? Paper, pin this. It is pinned. Need the other view. Oh God, now you guys are all big. Okay, there we go. Okay, so essentially what we're going to do then is we're going to take this ellipse, okay, build a bunch of rectangles in here, add up all the rectangles, right, and then multiply by 4. So here's what I'm going to do. I'm going to cut to the chase, because we've been talking about Riemann sums for a long time. So what would you do? You'd say length times width, length times width, length times width, and that's a sum. And then the limit is n goes to infinity. And then we'd use the notation of the definite integral to write it as a definite integral and solve it, hopefully not by finding that big long sum, but rather by anti-differentiating, use the fundamental theorem of calculus. We good, all that? That was like twice through, right? Don't forget all that stuff. It's kind of important. All right, so here's what I'm gonna do. I'm gonna cut to the chase. This, oh, maybe we didn't look at that. A was stretching in the x direction, if I remember right. Right? A is stretching in the x direction, and B was stretching in the y direction, and I just left it 1 for now. So we'll just do that specific one. So I'm saying this is stretched out to, say, 3, 0. And this is stretched up to, say, 0, 1. Sounded like someone coming or going. I don't know who that was. Okay, so I would like to do the integral from 0 to 3, right? So we're going out this way, of length times width. So the height, right, is given by f of x, and the width, right, is given by delta x. So when we stick it in definite integral notation, someone's feedbacking on us. Figure out if that's you and stop it. How to do that. I think I got the dot cam shut off, so because I had this giant feedback loop with 2 people signed into the meeting, but I think on my end, I think it should be clear. All right, so it looks something like this. So the question is, how do we get the height, right? And so the height, this was our curve. It was x squared over a squared plus y squared over b squared equals 1. So I'm thinking the height would be the y, right? So we're going to have to solve for y. So let's see, that would be y squared over b squared. Now, of course, it's a lot more annoying to do this with a and b being a and b, and a lot easier to do this if a is 3 and b is 1, right? So maybe we should just do the specific case with specific numbers and then go back and do the general case later, right? Or we can just carry the a and b through, and then when we get to the end, we can plug in the 1 and the 3. Right? So we can either do it general or specific. I think it's probably easier to put in the 1 and the 3 right now and just do the specific case, right? And then clean it up later. Sound okay? All right, that's what I'm doing. So B was 1 and A was 3. So I'm thinking y squared equals 1 minus x squared over 9. Making y equal to the square root of 1 minus x squared over 9. How'd I do on my algebra? Still okay? I'm kind of thinking that online's not gonna like significantly improve it, which means I'll probably still make mistakes. So you need to shout it out when I make a mistake, right?
It looks pretty good.
Okay, that has not changed. So make sure you're still doing that. All right, here we go. 0 to 3. So I've got the square root of 1 minus x squared, that's it squared, over 9 dx. So if I could find this integral, I would have a quarter of the area. I can multiply it by 4. I'd have the area of an ellipse. How are we doing so far? Good? Okay, if not, so then the question is, can you do this integral? And the answer is, man, it'd be a lot easier if there was, say, a 2/9 x hanging around on the outside, because then it would be a chain rule. Well, minus 2/9 x would even be better, wouldn't it? And then it would just be a chain rule. It's to the half power, it'd be to the 3/2 power. We'd just use the chain rule backwards, we'd be done. But I don't see the rest of the chain hanging around on the outside. So chain rule is not going to work. Okay, so try something else. All right, what's next? Integration by parts. By the way, Preston, who we haven't seen on the chat yet, had a super awesome solution for sine squared. It was really slick. using integration by parts. Like all the rest of you just use the half angle formula. And he used integration by parts. And sometimes that, remember I told you one way is usually faster or cleaner than the other. And he was able to do it in a really slick way that I hadn't seen before. It was really nice. Maybe I can find that and post it for you. It's really cool. Anyway, this isn't an integration by parts because, of course, there aren't two factors, right? And it looks more like a composition to me, something inside of something else, not something multiplied times something else. Now, you could force it by saying one of the factors is 1 and one of the factors is the square root of 1 minus x squared over 9. But I just don't think you're going to make a lot of progress going that direction. So I'm thinking not integration by parts. I'm looking at it and I'm saying it doesn't look like a section 7-2 problem because those were all sines and cosines. Those are trig integrals. It's not trig. So what do? How about a trig sub? Okay, and the reason I'm thinking trig sub is because it's got some squares inside and a square root of something squared. And if I could write that 1 minus x squared stuff as say 1 minus cosine squared, then I could write it as sine squared. I'd take the square root of the sine squared. I'd end up with just a regular old sine. It'd be easy. Okay, so what's causing us grief is the root, and we want the root to go away. And the way we're going to make the root go away is to turn this into a trig integral and then use the Pythagorean theorem. Okay, so now it only comes down to, well, which sub, right? Do we let x be sine? Do we let x be cosine? Do we let x be secant or tangent? And then probably, given that we're time crunched and all, we probably won't let it be cosecant and cotangent. But you know, if you can do secant and tangent, you can do cosecant, cotangent, right? We just don't see those as often. So let me try the easiest one. It turns out in this case that x could be sine or cosine, doesn't matter. Because of course 1 minus sine squared is cosine squared and 1 minus cosine squared is sine squared. This is annoying for your instructor who has to grade all your papers because half you'll choose one, half will choose the other, and then I have to nitpick through to grade it, right? But so make sure, and I don't know how we're gonna, you know, if you just print it out and do it with pencil, make sure you show your work. If you're trying to do it with your finger on your iPad, a little harder to show your work, right? But do your best to let me know what you did. So I'm gonna say, go ahead.
So is that the case for most of them where you can just flip-flop sine and cosine, or is that just a random, like, rare exception?
No, that's usually the case. It doesn't make any difference. And I know yesterday in that little suggestion, it said always choose sine in this case, right? But it turns out it doesn't matter. You could choose cosine too. You just get an extra minus sign to deal with when you took the derivative. So how about x is, how about 3, right? How about 3 sine theta? I'm kind of thinking we're going to need a 3 because of the 9 in the denominator, but I'm just kind of guessing. I haven't done enough of these to have it memorized exactly what it should be. Should it be 3? Should it be 1/3? I don't know. We're going to try it, and then we're going to go forward. We might have to fix it. Okay, so if that's true, then the dx would be derivative of sine is what? Still cosine?
Cosine.
Yeah, derivative. Okay, so 3 cosine theta. And so let's see if we can substitute. Now, check this out. Remember these limits up here? We didn't have limits yesterday, but these limits are in terms of what? Yeah? This is x equals 0 to 3. So we're going to have to change everything into thetas if we're going to go to theta. Okay? So if we want to change and change back, we don't have to change the limits if we change back to x's before we substitute. If you're going to substitute in the theta, you're going to have to stick the x's in, or you're going to have to change these x's to thetas first. So let me change everything. All right. So now, if x starts at 0, right, what does theta start at? And you go, boy, that's ugly. Put a 0 in where the x is. Divide by 3. Do you know any angles whose sine is 0? Yes.
0?
0 would be a good one. And then if x is equal to 3, then let me write it. I'll go over here to the side, scratch it out. If x equals 3, then 3 equals 3 sine theta. So 1 equals sine theta. So theta equals inverse sine of 1. Do you know any angles whose sine is 1? Yes, you do. Pi over 2. Straight up the sine is 1, right? If that's still bothering you, you know, unit circle, right? Cosine, sine. Yeah, it's a unit circle. So when it's straight up at pi over 2, it's going to be 1. So I'm thinking theta goes to 1. Yes? All right. Square root 1 minus x squared. So you got to stick in your x. 3 sine theta, right? Squared over 9. And then in where your dx is, you're going to have to solve for dx. So dx looks like 3 cosine theta d theta. So at this point, you got to be a little bit careful to, you know, not let your 3 cosine theta fall into your root. So you might want to put it in the front. If you're, you know, you do a bunch of these problems and you can anticipate it's going to go there, you could leave some space and then put it in the front, then it won't fall underneath, right? That, I see that a lot. You'll get going along and the 3 sneaks under the radical and then that's a problem. All right, well, let's see if we can do this integral. So now you change the problem into a new problem, which to me looks worse. It's still got a root. It's got a bunch of trig functions in it now, but maybe if we clean it up, it'll make it easier. So I got the integral 0 to 1. These are thetas now. This is the square root of what is this? This is 1 minus 3 squared is 9. So I got 9 sine squared theta over 9, right? And then maybe to be, oh, well, I didn't leave room. I was going to move it to the front, but I didn't. So I'll move it to the front now. Here comes the 3 all the way out. Here's the cosine theta in the front. Okay, 9 cancels with the 9. You recognize 1 minus sine squared?
Yes.
Cosine squared.
Yeah, I'm hoping. That was the whole point of the exercise, right? I mean, that's why you chose to substitute that in the first place. So that shouldn't be a big surprise. And of course, it's right over here in the triangle. Cosine squared plus sine squared is 1 squared. So 1 squared minus sine squared must be cosine squared. So I'm thinking this is cosine squared. So this is a cosine squared under the root. So maybe I'll just write that. Although you probably could just simplify that, right? Square root of cosine squared.
It's cosine.
Yeah, and you sticklers are going to be complaining that, of course, that depends. It could be positive or negative, blah, 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 blah. But if we're staying over there in the first quadrant, we're only worrying about the positive ones anyway. Okay, if you're doing this in general, then you say, yeah, well, it only works on the domain and there's going to be certain points that might be a problem. And, so you might have to dig into the gory details of that. And we avoided it by staying in the first quadrant in the first place. So square root of cosine squared is cosine. We have this cosine, that's cosine squared. So that's 3 times the integral of cosine squared theta d theta. I'd love to show you Preston's really cool way of doing this. He let one be cosine, the other be cosine, and used integration by parts with a wraparound. I'm going to let you try it. It turned out pretty slick. But I've always done these using the half angle formula because I just took the time to memorize the half angle formula, so I might as well make some use of it because I'm kind of thinking if you don't use the half angle formula right now, you're never going to use it in your life. So now would be a good time, right? So do you remember what it is?
1 plus.
1 plus, right? The cosine of 2 theta, right?
All divided by 2.
Divided by 2. Okay, so the formulas aren't too bad because one of them's plus and one of them's minus, and they look exactly the same, right? For sine squared, it's 1 minus cosine 2 theta over 2. And for cosine, it's plus. So you just have to remember the plus or minus. And of course, you already know I can't do that. So, you know, you're going to, you know, but if there's going to be a mistake, I'm probably going to circle that plus sign right there and put a question mark by it. And unfortunately have to take off a point, right? That's going to happen from time to time. Okay, so I'm gonna pull the 2 out and move this up. I'm running out of room here. Okay, whoops, low. Uh-oh. You get it?
There you
go. Okay, whoops. So 3/2. We still got the integral, and then we've got what, 1 plus cosine 2 theta d theta. So the integral of a sum is the sum of the integrals. Integral of 1 is what?
Theta.
Just regular old theta plus 3/2, right? Integral of cosine. So some function whose derivative is cosine.
Sine.
Sine, right, of 2 theta. And when I take the derivative, I'm going to get an extra 2. So I'm going to need a what in front here? Didn't leave much room for it. I'm going to need an extra 2, so I'll put it with this one. We still doing okay? From 0 to 1. Okay, notice that I'm plugging in for the theta, so my limits have to be thetas, but we changed them to thetas, so we're in good shape. Put in 1, what do you get, 3/2? And then we've got plus the sine of 2 theta. What's going on here? I'm feeling kind of bad. How come? The sine of 2, that seems to be giving us a little bit of grief, doesn't it?
Yeah.
Yeah. So there's something wrong because I'm pretty sure the answer doesn't have a sine of 2, right? What does the sine of 2 look like? Right? The sine of 2 is 2, you know, is 2 degrees, or if you're in radians, 2 radians. So 1 radius, that much, wraps to about there. 2 wraps to about there, yeah? 3.14 wraps to here. So good grief, you're talking about the sine, you're talking about this length right here, the sine of 2. That just doesn't seem like it could be right. So it seems like we made a mistake somewhere. Did you guys catch it? You didn't shout it out. If you did catch it, you guys just listening in could type, yeah, you know, you should be more careful. Where is it? Come on. I'll give you a hint. I'm gonna have to get you up to speed on catching my errors on online instruction. Yeah. Look, we calculated it. It was supposed to be theta equals pi over 2. We said straight up is pi over 2. But then when I wrote it over here, what did I write?
Oh, you wrote 1.
I wrote the 1 again, right? It wasn't supposed to be 1. It was supposed to be the inverse sine of 1, which should have been pi over 2. So I think right here where I wrote it, I was supposed to write pi over 2. Does that make sense? Are you with me?
Yeah.
Okay. Does that ever happen? Yes. I mean, I wasn't demonstrating really how to do it wrong, but I'm guessing, since I've seen about 1,000 of these, that somebody's going to do it wrong. So how are you going to know that you did it wrong? Well, when you get down here and you try to plug in the sine of 2, it's not going to make any sense. So go back and try to figure out what happened. Yeah. Okay. So I think this should have been pi over 2 all the way down. Pi over 2, pi over 2, pi over 2. Hey, let me ask you this as well. If you were trying to find the area of a circle, you'd sure expect what to show up?
Pi.
Pi. It's pi r squared. If there's no pi in the answer, you're kind of probably thinking this isn't working out real well. Does that make sense?
Yeah.
Okay, plug in theta now. It's 3/2 times pi over 2, yeah?
Mm-hmm.
Okay, plus 3/4 of the sine of 2 pi over 2s. Well, 2 pi over 2s is pi, and the sine at pi is what?
0.
0. Okay, so there's the first part. Minus what we get when we plug in 0. Well, 3/2 times 0, right? That's going to be 0. Plus 3/4 times the sine of 2 times 0. Well, 2 zeros are 0, and the sine of 0 is
0.
0. Okay, so that's 0 and 0. So we're subtracting 0 and we're adding 0. So it looks to me like the answer is 3 pi over 4. Okay. Well, if everything's right, that seems possible, I guess. Here was our picture up here.
And wasn't that only a quarter of it?
And that was only a quarter of it. So the whole
So
thing,
3 pi.
so the whole thing, right, was 3 pi for the whole ellipse. So how do we know if that's right, wrong, accurate? I'm gonna flip over. What if it would have just been a circle, radius 1? Then it would have been what? Pi r squared,
So
better known
yeah,
as what?
be pi.
Okay. What if it would have been a circle, radius 3?
9.
9 pi, right? So I'm kind of thinking that if I ellipse this thing so that it goes out to 3, but only up to 1, then that means that the big circle would fit around it like this, right? Sorry about the messy drawing. And the little circle would fit inside of it like that. So I'm kind of thinking the ellipse is going to be somewhere between pi and 9 pi. So
Yes.
the question is 3 pi right? Well, I don't know. That one's pi. If I put another one right here and another one right here, does it look like it could kind of be 3 pi? It kind of looks like 3 pi, doesn't it?
Mm-hmm.
Okay, I would say our answer is reasonable based on just this picture. If you want to know, even more if it's reasonable, well, we could just switch back to, here. And what would we do? I don't know, type this, if it's working. Integral from 0 to 1, to 3, below, to 3. Where was it? I don't know if you guys can see it anymore. I think it's back here. Here it is right here, right? Square root 1 minus x squared over 9. X squared over 9, right? Dx. Whoops, got to get outside. Dx. How about that number? I don't know. If that number was 3 pi, we'd be in pretty good shape. But you said that number was what?
Oh, yeah.
Oh, yeah, that was only a quarter of it. So we need 4 of those. Hey, it's looking pretty good to me. So what did Desmos do when it calculated this? Do you remember? It built rectangles, right? This is built, except it didn't really. It did some internal thing kind of more efficient than rectangles, but basically it built rectangles and estimated it. Okay, and that's what you get when you add up a bunch of rectangles. That's what you get, when you do it exactly, I'm kind of thinking maybe we got the right answer. Feeling good? Okay, so it begs the question then, what if I stretch this out a little bit further, right? What if I make this go back this way? So what's the difference? I'm thinking that the difference would be when we solve this for y, right? We were going to get x squared over a squared is down here still, right? X squared over a squared. So that goes on this side. That's 1 minus that. But then notice that since we solved for y, we got to multiply times b squared. So we're going to have to multiply times b squared. And of course, you could write this, cleaned up a little bit better than that. You could distribute, or you could factor out this b squared over a squared. So I might rewrite it like this. Let's see if I could rewrite it. I might factor out this a squared by putting an a squared right here. Oops, an a squared right there over, right, a squared. Now I got an a squared in the bottom. So I'm going to factor it out. I'm going to put it with this b squared. I'm going to pull them all the way out to the front. So I'm going to get b over a. I don't need the parenthesis, I don't think. B over a. That gets this b squared out, yes? It gets this a squared, gets this a squared out of the denominator. And it gets this one out of there too. And I don't need these parentheses. So I'm kind of thinking, same. How come it came out negative? Missing some what? Square root of something squared, need what?
Oh, absolute value.
Need absolute values. So what I do is if you wanted to do this like in a math conference, you'd want that number to not say the area is negative 15, right? You want to clean that up. You want all the details exactly right. But if you're just looking at it, you're going, well, why is it negative 15? Because b over a, I'm in the wrong quadrant. The b's and the a's aren't quite right. Does it matter? Not really, because the area must be the positive 15. Wouldn't you agree? But I suppose we could clean that up if you wanted to be, really accurate here. So again, I don't know if I would go for the full-blown accuracy. I'd kind of go for the, I understand this, and then I can interpret what the solution is. Is this looking okay? Notice there's one more problem. What is it? This goes from 0 to
3.
a now, yes?
Yeah.
Because we chopped this up all the way out to a. I'm kind of thinking that this is the formula, and check out what happens now. So we get the area this way, and if we let b go, we got the area this way. So now we've got the sort of the whole thing going on. So there's our sort of our cleaned up version in general. The question is, what would happen if we went all the way through this in general? Okay, and I'm going to say the 3, right, shows up from the a, and what didn't, oops, sorry, I can't see it. I'm gonna have to stop sharing this so I can see this, so I can see if it's in focus, which it isn't. Okay, the 3 showed up from the a. What is not so obvious is that the 1 from the b also shows up here. So I'll let you carry that through when b is something other than 1. And we end up with a, b, pi. Cool, huh? And when a and b are both the same, we sometimes call them r, and we'd end up with pi r squared for the circle. Pretty slick. Area of a circle. This is like a huge day. This is like the coolest thing ever, because you only knew that because your 3rd grade teacher told you, and now we actually proved it, right? Which is kind of a cool thing. So you don't really have to depend on other people. I mean, we're like on the breakdown of society right now. You're already locked in your house. I mean, if the internet went down, what would you do? You'd have to just sit at home and prove this for yourself, which you can do now, right? Which is pretty cool. Okay, so here's an example of where trigonometric substitution is going to be a skill that you use to get the integral inside of a bigger context. Like you're not going to do integrals stand alone by themselves, other than on a quiz that I give you, you know, or if you're just doing them for fun, right? Usually what's going to happen is you're going to be solving a problem, like you're trying to find the area of an ellipse, okay? And then it gives rise to some kind of an integral, and then you need some techniques to be able to solve that integral. The easiest one, estimate it using Desmos. But if you need an exact answer, then, I don't know, look it up in an anti-differentiator like Symbol Lab or MAT or Wolfram Alpha. Okay, but if you want to do it yourself, well, then you need one of these techniques. Okay, so all the applications that we've seen so far, they don't go away. It's just now some of the applications are producing integrals that are going to require, let's call them more advanced techniques, techniques from chapter 7, right? And in this case, what we'll call it is a trig substitution. And then that's it for this section, 7.3, other than just to practice. So what do you think? Do we need to practice on a couple more? Did you try some on the homework? Do you have some questions that you're stuck on?
Hey, can we try one more, please?
Yes, let's try one more. I would like to do one more, maybe without the whole context, and just do the integral part, right? Because I'm trusting at this point, if you had to find an area, you could set it up right as a Riemann sum, and you could also substitute the values and do the calculation down at the bottom. As we've seen, you need to be a little bit careful, but it's just being careful. It's not being thoughtful, right? You already kind of know how to do it. So,
the one more we try. Can we try from the homework?
Okay, give me one from the homework.
The integral from 0 to a.
0 to a. Ugh. All right.
5x squared.
5x squared.
Root a squared minus x squared dx.
A squared minus x squared dx. Yeah, I could definitely do this one, but let's at least get this one set up. Okay, because I'm seeing something, I'm seeing a new problem on this one that I didn't see on the one we just did. Hello, come on, camera. It's not liking it. I'm gonna have to wiggle it over here. There we go. Okay.
For starters, it looks a lot like the last one we just did.
Yes, it does. And so what would you try? Let x be what?
Sine of x.
Yeah, I would even say a sine, maybe.
Oh yeah,
theta,
a sine of x. Or a sine of theta.
And because they're trig functions, I'm going to probably use thetas. The book used theta. Yesterday I used u. Doesn't matter. What I'm seeing that's different about this one, though, is notice the 5x squared. Wouldn't that have been nice if that was a minus 2x instead of a 5x squared? Would have been sweet. Would have been chain rule. Okay, but the only difference in this problem and the last one is that we're going to use the same trig sub, and we're going to have to deal with the 5x squared. So let's see if we can do the sub. So if x is that, dx must be a cosine theta, d theta. You see why maybe it's nice to choose sine instead of cosine? Because right here, right, if you chose cosine, then you get an extra minus sign. Right? And then you have to deal with an extra minus sign running around. And I always lose those, so I usually choose sine. All right, so here we go. All right, so these limits, 0 to a, right, are in terms of x. So what does theta go from when x is 0?
0.
So x is 0 right here. Divide by a. Do you know any angles whose sine is 0?
0.
0. And this one is theta equals, well, when x is a, I divide by a, I get 1. Do you know any angles whose sine is 1? Yeah, let's write it down correctly this time. Pi over 2. Okay, So 5x squared, I'm just going to go ahead and square it. 5a squared sine squared theta. And then in here I get square root a squared minus a squared sine squared theta d theta. Not d theta. Why not?
Where'd you get the sine square on the outside?
Okay, in for the x right there.
Oh yeah. Okay, never mind.
You put this. Okay.
Yeah.
So then in for the x right there, I put this again and got a squared sine squared inside right there.
Yeah.
But I'm seeing a problem. This is the second problem that I see a lot. But what is it? I fixed the limits of integration correctly this time. I got these right. But what's wrong?
You need to
The derivative of x?
Yeah, this isn't right, is it? dx isn't d theta. dx is equal to what? A cosine theta d theta. Okay, so don't forget to put it in, and that's it. That's all the errors I ever see. So and the rest is just algebra. All right, so let's see if we can clean this up. There's an a squared there. There's an a squared there. I'm going to factor it out. I'm going to take the square root. I'm going to remember that I might have a problem if a is negative, but I'm not going to care. And I'm just going to put it with this a right here. Okay, so here's what I got. 0 pi over 2. That's 5a cubed now. Okay, and then I've got this sine squared, right? And now what's left in here? 1 minus sine squared. I still have this, oops. See that a right there? I could put that a right there with these a's too, and I would get a to the fourth, wouldn't I? Okay, there's 2 right here. There's 1 inside. There's 1 right there. So a to the fourth, okay. And then I've got a cosine theta d theta out here. 1 minus sine squared is what?
cosine squared.
Cosine squared, square rooted is cosine. So I've got 0 pi over 2, 5a to the fourth, sine squared. There's a cosine here. There's a cosine here. So I got cosine squared. And guess what? The 5a to the fourth can come out in front, and the rest of it is a section 7-2 problem now. So how do you do those kind? You try to keep one, but they're both even, right? So you're going to have to use half angle formula. And because it's a fourth power, it's a sine, it's a fourth order, you're going to have to use it twice. So let me kind of get you started now. That was it for 7-3. This was all 7-3. And now we're on 7-2, right? So 0 pi over 2. I can pull out the 5a to the fourth. And then in here, I'm going to put 1 minus cosine 2 theta over 2. And in here, I'm going to put 1 plus cosine 2 theta over 2, right? D theta. And we're not done. We got a long ways to go yet. Okay, multiply those guys together, you're going to get another cosine squared. So you're going to have to use the half angle again. And then I think it'll fall out after that. Don't forget, plug it in the pi over 2 and the 0, and then you get all the way to the answer. How are we doing? Good? Okay, so in terms of section 7-3, the hard part was, do I recognize that I should probably use a trig sub? And which trig sub? How about a sine theta? Okay, if you knew that, if you get to there, then like if you get to here, okay, then you mastered everything in section 7-3 except for the details. But of course, this is just going to make a new integral. And the new integral, right, is going to require some section 7-2 stuff to be able to solve it. So 7-2 never goes away. And of course, you know that. It's all cumulative, right? So enjoy it, because this is when you get to use all the math you've ever learned in your whole life. And after this, who knows? Maybe you'll be teaching math online to people. You want another one? Give me another one. What else you got? Here, let me give you this one. What do you guys want to do with this one?
Can let x be two tangent theta.
Two tangent theta, that's the red herring, of course. Because you're thinking, this is causing me some grief. If it's 2 tangent theta, then I would have 4 tangent squared theta. I'd factor out the 4. I'd take it outside the square root. It would be a 2. I'd have tangent squared plus 1. And you may be thinking 1 squared plus 2 plus tangent squared, right, is equal to secant squared. All right, who's going crazy on their mic? Somebody who's not listening. They just left their thing on to make them think that they were in the meeting. What would you get down here? You get a secant, wouldn't you?
Mm-hmm.
2 secants, in fact. What would you get up here? Ew, a tangent. Now you get a tangent over a secant. Is that easy? I don't know. Maybe it's easy. Could you keep going and try to make it work out?
A secant is just 1 over cosine. So
Yes.
then if you multiply by the inverse, the cosines will cancel out and you should just be left with 2 sine, I think.
Isn't that just this problem though? Am I wrong?
Aha.
Yeah, this is
Curtis is determined to continue on and will make it to the end. But somebody else might see, wait a minute, if this was just a 2x, isn't that just the derivative of the stuff inside? Isn't this just a chain rule? So does it matter? The answer is no, it doesn't matter. You can do this the way you said with the trig sub. It's more steps, but you're going to get there, okay? But if you recognize it as a chain rule, then you might get there faster. So if it's chain rule, I'm kind of thinking it's to the negative 1/2 power. That means it was probably to the positive 1/2 power before.
Mm-hmm.
And that means that if I took the derivative of this to check, I'm getting 1/2 of this stuff to the negative 1/2 times the derivative of the stuff, which is 2x. The half and the 2 cancel. Done. But I'm still not, I'm still convinced that if we let x be 2 tangent theta, we're going to get to the same place. It's just going to take more steps. Okay, so don't forget the things you learned before. Kind of run down the list in your head of, do I recognize it? Is it a chain rule? Is it an integration by parts? However, I kind of baited you a little bit because, of course, this is in the section on trig sub. So you're thinking I should use a trig sub, which is a good thing to be thinking. How are we doing? Good on this one?
Mm-hmm.
I actually have a question.
Okay.
It's another problem. It's really similar to this one, though.
Okay, give it to me.
It's basically the same problem, except instead of x in the numerator, it's dx.
It's just dx only?
Yeah.
Yes, this one now.
Oh, no. Yeah, that.
Oh yeah.
Now you mean just this problem.
Mm-hmm.
And whether the dx is in the top or a 1 in the top, it's same. Okay, now this one is definitely not a chain rule. Okay, so you
No,
can't go the shortcut way here because you need a 2x in the numerator and there isn't one. Okay, so now we do have to sub. So now I really am going to let x be 2 tangent theta.
Now, also, it's the definite integral between 0 and 2.
Okay, so then dx, do you remember the derivative of tangent?
Secant tangent.
Secant
Or
close.
secant squared.
Secant squared, yeah. So then what do we got to do? We got to sub, right? So here we go. These are x's. We want thetas. So we're going to say when x is 0, when x right there is 0, what's theta? So you go 0 divided by 2 is 0. Do you know any angles whose tangent is 0? Here's the picture back up here.
Yeah, it'd be 0.
0 is correct. And then theta equals, well, when x is 2, 2 divided by 2 is 1. Do you know any angles whose tangent is 1? It looks like that one. Pi over what?
4.
Oh, come on, camera. This length right here has to be 1. What angle?
Pi over 4.
Pi over 4. Okay, whoops. Down here. All right, 1 over square root. All right, I'm going to figure out who that is. Who is that?
I'm going to water. You guys do anything? No. I don't know.
Okay, so I'm gonna go to Costco right now, so I'll pick.
Okay. Come on, watch out. So, no, sorry. Come on.
Oh. Maybe.
It's some dude named Hamza.
It looks like it was Hamza. All right, if you want to talk Hamza, you got to quiet that background noise down and then turn your mic back on. All right, 1 over, let's see, square root of 2 squared, right? So 4 tangent squared plus 4, and d theta was what? Or dx was 2 secant squared theta d theta. So now I'm thinking 0 to pi over 4. In the top, or in the bottom, we're going to have a 4, factor out this 4, take the square root, get a 2, cancel it with this 2. Everybody okay with that?
Yep.
Okay, so in the top, I've got a secant squared, and in the bottom, I've got a square root of tan squared plus 1. So what's that?
Secant squared.
That's secant squared. So whether you do several of these steps in your head or not, kind of up to you, how much you want to write. But what I do want to see on your paper, so I know what you did, you got to at least tell me what x was, okay? And at least set up the integral. But if you want to combine steps on the algebra because you can do it fast, okay, that's fine.
Do we have to change the x's to thetas, or
No,
can we go back
you
to the end?
you can substitute the x's back in and then substitute the values in terms of x if you want to. So
Okay.
you either have to change the limits here to thetas and then put them in for theta, or you got to, after you do the integral, put the x's back in before you put the x's in.
Okay.
Okay, so you can do it either way, whatever's easier. So tangent squared plus 1 is secant squared, square root is secant. There's 1 in the bottom, 2 in the top. That leaves secant. Okay, now we got a problem. Well, we might have a problem. How do we do this one?
Don't you do that weird trick where you times it by secant theta plus tan theta?
Yeah, that would be it.
Oh,
That would be the weird trick. Or you wait until Monday or Wednesday of next week, probably Monday, and I show you another way we can do it. In other words, I think this one should be on our list of ones you have memorized. And
So
maybe you
it's
memorize the trick or memorize the answer. It's all the same because the answer gives you the trick. All right, so here's what I'm thinking. Isn't it the log of secant plus tangent?
Yeah.
Yeah.
Secant theta plus tangent theta. I think that's it. And of course, that gives you the trick because the trick was multiply by secant theta plus tangent theta, and it's going to work out.
Mm.
Okay, from 0 pi over 4. And then, of course, I can let you figure that out to the end because it's going to be the log of some nasty stuff. You're going to get some kind of a decimal anyway. Looking okay?
Mhm.
Okay, there's one where we substituted a tangent in. Of course, there's one more where we could substitute a secant in. And of course, then there's a bunch that we didn't even look at that are in terms of cosecant and cotangent. But it turns out that that's just the same thing, just messy. And it turns out that cosecants and cotangents don't happen as often in real world problems that you're likely to run into. But it would just be the same thing with some minus signs. Okay, so we're not going to focus on the cosecant and cotangent kind. We'll just work on, you know, the sine, cosine, secant, and tangents, like we've been doing. Okay, how are we doing? Good.
Good.
I've got a couple more. I think yesterday I pointed out like what to do on here. Let me write down one more. Here's one more. I think we had it yesterday though. What if you have, right, this guy, then what should we do on that one?
Oh yeah, that's the complete the square.
That's got to be a complete the square because it's got to be in vertex form. Otherwise you can't do the substitution. You don't have the Pythagorean identity. So you're going to complete the square on this one. And so you got to remember, you might want to just step aside, complete the square off to the side. Okay, but what I'm thinking is factor out the minus, you know, that might be a good idea, or right? And then x squared plus 2x, what would that be? Like plus 1, I think. Can you do that in your head? I don't know, maybe not. Here's what you do. I don't know if I can do it in my head, so, but I bet with a little bit of effort, you could probably get it all worked out like this off to the side with some scratch paper. Okay, so I'm not going to go through all the steps. I can work it out with you later if you're having trouble, but I'm kind of thinking that if you completed the square, you would get that.
Yeah.
See it? True?
Yeah.
Is it right? I think it's right. It's easier to go forward, right, and expand and check it than it is to kind of go backwards. But with a little work, we can go forward and backwards. And if you could do that, you can tutor in the math solution. I'm kind of hearing that you can tutor online now, make some big bucks from home. So if, you know, worst case scenario, we'll hook you up with that. Okay, so now what? So now a couple things. First, you can let you, if you're a big substitution person, let u be x plus 1 and change everything to u's, because then you'd have a square root of 4 minus u squared down here, and then it would look more like, you know, our real problems that we've been doing before. So what does that mean? Well, if u is x plus 1, then x is u minus 1, and then this is the square root of 4 minus u squared. And of course, dx is equal to du, because the derivative of x is 1. So now you changed it to u's, and now you're going, oh yeah, now this is looking a lot like, so what do you call that? I don't know, I call that a u sub.
And then it's
Yeah.
not changeable.
Right? And then that one is looking a little like a chain rule, except for that minus 1, I think, is causing us grief. So you could split the fraction. That's kind of a cool one. And you could put the u over the square root of 4 minus u squared and do chain rule on the first part. But to do the minus 1 over square root of 4 minus u squared, you're going to have to do a trig sub. You guys hear what Katie was saying? She wants to split it into 2 here. She wants to do this piece first because she recognized it as chain rule, and then this piece second because it just looked easier to split it apart. Okay, but in the end, you're going to have to do a trig sub on this. So you might as well just do a trig sub on this without splitting it. Although it doesn't matter, you can do this one by chain rule, right? And then this one if it's easier. How are we doing? Everybody on board? What do we want to substitute? Let u be what?
Yeah.
2 sine theta.
Yeah,
Right
2
on.
sine.
I'm getting 2 sine theta. du then is 2 cosine theta d theta. And so then what do? We got to put it in for all this stuff. So we get the integral, we got a 2 sine theta on the top. We got a 2 sine theta squared. So that means we've got a 4, square rooted is a 2, right? Then we've got the square root of 1 minus sine squared. 1 minus sine squared is cosine squared, square rooted is cosine. Yes? If I'm going too fast, then work it out with pencil a little bit more slowly. And then when we substitute for the du, we got to put in what? 2 cosine theta, right? D theta. That's kind of convenient. Integral of
just
2
10
sine theta, that should be pretty easy. Do you know any functions whose derivative is sine?
Yeah, negative cosine.
Negative cosine.
I'm hearing negative cosine from, and now I don't know what these limits were, right? If there were no limits, now you got limits that were originally in terms of x, way back up here. If there were limits, they were in terms of x. Then you switched them to u's. Then you switched them to thetas. So if these would have to be plugged in terms of thetas, or you'd have to go all the way back to x before you plug them in. Does that make sense? Fortunately for us, it was an indefinite integral, and we could just add a plus c and call it good. That seems like a crazy answer. Does that seem right?
That was only half of it, I think.
It seems kind of easy. That was only half.
I think he only did the first integral.
Oh, I only did part of it. Okay. So what part was that? That was the chain. That was the chain rule part, right? I had only done this half. Yeah, I took care of that one. And you'd have to take care of this half.
Yeah.
Okay, because I don't think that's the answer, is it?
No.
I don't think so. No. So so keep going, right, and do the rest. But I'm going to kind of bail because I think you can kind of see what to do. The trick on this one is if you get something that looks like this, if you get something that looks like this, you should probably complete the square. Okay. That is all. That is all that there is in this section. So I'm going to leave it to you to do the homework problems. If you're stuck on a particular homework problem, you can send me an email or you can stop by office hours. I will be online. And then we're going to move forward. So on Monday, I want to do the last technique from chapter 7, which should get us a cool way, a better way of getting the integral of secant rather than, remembering that trick of multiplying by secant plus tangent over secant plus tangent, right? That was kind of clunky. So I think we'll come up with a new way. And we're also going to get a bunch of additional integrals that we currently can't solve with section 7.4. And then of course there's more and more and more techniques, but we're going to call it good after that. Okay, so we got one set of techniques left. It's in 7.4. 7.5 is everything all mixed together. And then what I would like to do is a quiz of some kind, somewhere probably Friday of next week, because I want to practice, like, how are we going to do quizzes? So I might give it to you in Canvas. I mean, I want to do it on something small. So we'll just do a small little integral quiz, probably Friday of next week, just so that we can kind of figure out how it is that we're going to do tests.
Will that quiz be more like a take-home or more like a traditional quiz?
No, it's going to feel a lot like a take-home. Okay, I'm going to find a way to send it to you in Canvas, and then I want you to find a way to do it, which might mean print it, pencil, scan it, or it might mean, download it and do it electronically, fill it out with your Apple Pencil on your tablet. But I want you to have some experience figuring out how it is that you're going to get a test from me, right? Fill it out and get it back to me. And I want to do it just with a small quiz so that we can kind of practice, before we, get down the road and need to do a test and don't know how to do it. Okay? That's the plan for next week. You guys probably saw, I don't know if you did see, we've got some mixed messages coming from the chancellor. They officially said that school's been postponed till April 6th. Please don't, I mean, you're welcome to just do nothing until April 6th, but we're not going to learn very much calculus if you do that. So, you know, for sure, please prioritize your health and safety first, right? So if you've got other concerns, you got things that are pressing, you're sick yourself. If you get sick yourself, we'll deal with it, right? We'll probably have to give you an incomplete. When you get healthy, we'll let you finish. But I want everybody else to get credit for Calc 2 and then be able to move down the road. So we got to meet the objectives for the course. We got to keep moving. So do the best you can. There will be nothing officially due until after April 6th, because that's what the chancellor said. But, and so I made all the due dates for all the homework the last day of the semester. So you got lots of time, but please keep working at it. You know, don't save it until the night before the last day of the semester, right? It'll be too much. Okay, so chip away as you have time and as it's possible. You know, come to office hours as much as, and class as much as you are capable, you know, it's comfortable for you. And I'll be happy to help as much as I can. Questions? Okay, seeing none, I'm going to let you jump out, and I will be here. I will be back. I'm going to take a little break and go get another cup of coffee, and then I'll be back in office hours at 10 if you want to stop by. If you're feeling like you just need some time to practice, you get stuck over the weekend, you can send me a note, or you can sign back in on office hours on Monday or come to class on Monday. Okay, well, have a great weekend, and good luck with doing the math.
Alrighty.
Bye.
Bye-bye.
See ya.